It's a pleasure to be with you, all of you today. And at this, being able to present at this conference, Statistical Learning Methods in Modern AI. Today, I'm going to talk about some work that we just started, and it's about how you think about the data you obtain once you've run an online decision-making algorithm, such as a reinforcement learning algorithm. And we'll do this in the context of digital health, in particular with heart steps. This is a physical activity intervention that's delivered via the smartphone and uses sensors on a wristband tracker. And the study's over, we ran this algorithm, and now we're asking, well, did this algorithm, this online decision-making algorithm, did it personalize treatment? Could we potentially overpromise what it's done? I'm fortunate to have a lot of many collaborators. These types of studies do involve large interdisciplinary teams. In particular, though, I want to put a shout out for Peng Liao. He's a postdoc in my lab in statistics. Kelly Zhang, who's a PhD student in computer science, and Zheyang Xi, who is an incoming first-year Harvard PhD student in statistics. All of them have worked on this project. So we're going to start off with a discussion of heart steps, the study that motivated this work. So this is, as I said, it's a coach. It's a mobile intervention. It's intended to be a coach for individuals who have or at high risk coronary artery disease, in particular people with stage 1 hypertension, high blood pressure. And it involved 3 studies. All 3 studies are over now. The first was for 6 weeks, and the second 2, which are highlighted in blue at the bottom of the slide, were for 3 months and 9 months. These are what I call micro-randomized studies. This should become clear what that means as we go along. And in the particular, the second 2 studies that merged together were personalized, and that should also become clear. So this activity coach includes a lot of different treatment components. We're going to focus on only one, the one that we used, the decision-making algorithm. And this is whether or not to send a contextually tailored activity suggestion. That is, it's a binary action, send the suggestion versus not. The content of the suggestion is tailored to the current sensor data. And you can see that here with this example. What happens is the phone would light up, the phone would ping, and you would get a message like this. And this message came in the morning on a work day when it was pretty cold. And so you can see how the message tries to frame that and just tries to get the individual to walk a little bit more than usual. It could occur, delivering or not delivering a message can occur at any of 5 times a day, and these are user-specific times related to that individual's the way they conduct their life. The reward, that is the outcome, is the 30-minute step count following each of these 5 time points. And the reason why it's over such a short period of time is because these activity suggestions are highly tailored to the context the individual is in at that moment in time. And they're intended to be used at that moment. So after the study's over, one sees data that looks like this. So on each user, you get these tuples, state, action, reward for some duration of time, depending on whether they're in the 3-month or the 9-month study. State is, or context is, it's composed of the sensor data that's being accruing from the tracker, and also sensor data from the phone, and adherence and so on. And then A denotes action, and that's the binary, deliver a suggestion versus don't deliver a suggestion. And we're going to talk about the algorithm that ran during the conduct of this study to produce A, capital A, deliver versus not, the binary action. And then subsequent to that, after that is the reward. And this is, in our case, it's the log of the 30-minute step count. These are highly skewed. Step counts are skewed data, and so the log is used. At the very bottom of the slide, I have just a small amount of notation, and we're going to use this repeatedly throughout this talk. That is the expected reward, expected log step count, expected reward given current state and action is denoted by this lowercase r function. It's a reward function. Okay, so we ran an online decision-making algorithm. In particular, it was a type of a Bandit algorithm. So it's a very special type of reinforcement learning. And the idea was to personalize treatment or delivering a suggestion, activity suggestion versus not. So based on that individual's current state, should you deliver versus should you not? And the idea here is to select these actions, binary actions, with the goal of maximizing the sum of the 30-minute step counts over the entire duration. Now, this is subject to a lot of constraints, and these constraints in the end mean that although we're interested in reducing regret minimization is not the goal in these kinds of studies. In particular, we want to be able to facilitate off-policy learning after data collection ceases. This will be critical. There's a wide variety of collaborators, and one has each one has a different type of analysis they would like to do after the study is over. There's also, from a scientific perspective, there's real problems with user burden and habituation. If you send too many messages, people become overburdened. They start to ignore the suggestions, and they may even delete the app. So in the second two studies, V2 and V3, that's the 3-month and the 9-month study, we used a generalization of a Thompson sampling algorithm to personalize action selection. We generalize this algorithm in a number of ways. I'm going to only talk to you about a couple in the next couple of slides. And the reason why I'm doing that is because I really want to get to the part about how do you analyze this? How do you think about this data after the study's over? So again, we used an online Thompson sampling Bandit algorithm or generalization of that to decide to choose AT equal 1 or AT equal 0. AT equal 1 means the suggestion is delivered, 0, it's not delivered. This is greedy. These algorithms are greedy in the sense that they only pay attention they only attempt to try and improve the reward, the immediate reward. They don't look into the future. They don't use predictions of the future and try to take into account future, say, burden and so on. In the actual algorithm, we did alter the reward to do a little bit of that, but here I won't talk about that aspect of the algorithm. This is an online personalization algorithm because the chance that an individual is delivered a suggestion depends on the accruing evidence of whether or not that suggestion is worth it in that individual's current state. So in these decision-making algorithms, there's always two elements. There's a learning algorithm, and all that is an incremental statistical method, some incremental method that you update as data accrues. In our case, what we used is a Bayesian linear regression, as a very simple form of a Gaussian process model for this reward function. And then the second element of these algorithms, these online decision-making algorithms, is the action selection strategy. So what strategy is one doing to experiment and be able to learn whether to send a suggestion? And what we're doing here is posterior sampling. So it matches the learning algorithm. In particular, we calculate the posterior probability that the treatment effect in the user's current context S is greater than 0. And then we take that probability and randomize the user, the individual, to getting a suggestion with that probability, that posterior probability. So this is called posterior sampling. Some points about how we develop this this algorithm, the Bandit algorithm. First is we use, as I said earlier, we used a Bayesian linear regression. In particular, the linear regression was for the treatment effect. So we have a low dimensional linear regression for the effect. That's this is the expected reward under send a suggestion minus the expected reward under not send a suggestion in the current state S. We modeled that via this linear combination. Theta is 5-dimensional, and you'll see what the features are on a subsequent slide. And we used an informative prior, and in general, that's how we are using reinforcement learning algorithms, is we use a Bayesian mindset and informative priors. And in our case, the informative prior comes from the first HeartStep study. And it's a Gaussian prior for the theta weights, the 5-dimensional theta vector. And in particular, the one thing I want to say here is the prior mean for all the weights is 0 except for the first weight, the first entry in theta, and that's positive. And this is going to be important as this is going to come into play later on in this talk. The action selection strategy, as I said, it's posterior sampling. Now, it turns out one has to give some thought to posterior sampling. It's not just a black, you just don't use it. And we realized this after we had started the study, and we had to restart the study. We had to adjust the algorithm and restart the study with new participants as a result of this realization. So I'm going to describe that to you here. So with posterior sampling, you select send a suggestion A = 1 with probability P, and this P is the posterior probability that the treatment effect in the current state is greater than 0. The question is this a good idea? So you see the first item 1 is in some states, this posterior, it's a Gaussian distribution, maybe will be really peaked around 0. What that means is this posterior probability will average at 0.5. Is this a good idea? Do you want a probability that averages around 0.5 when the learning algorithm is indicating there's no effect of sending a suggestion? In some states, so number 2, in some states, what we'll see is this posterior distribution of the treatment effect will be very peaked and will center around a mean much greater than 0. And so then the posterior probability is going to be really close to 1. Is this a good idea? Is it a good idea to always send the suggestion in that state, or to nearly always send that suggestion in that state? Well, neither one are good ideas. And in addition, we need to permit off-policy learning after the data collection. It ceases after the study's over. You facilitate this by preventing the posterior probabilities, in particular, the randomization probabilities, from getting too close to 0 or 1. And so you see this little graph, this little blue graph that I drew into this slide. So what we did was the x-axis is the old probability, the y-axis is the new probability. And if the posterior probability, the treatment effect is greater than 0, is greater than 0.8, we use 0.8. If it's lower than 0.2, we use 0.2, and then we have a linear interpolation in between. And it turns out that both that lower bound in the case of HeartStep's 0.8, and the upper bound was 0.8, and the lower bound was 0.2 in HeartStep's. These are determined. These can you want to be able to do off-policy learning, so that facilitates that. They're not too close to 0. But from a scientific perspective, these are determined using considerations of habituation and burden. And we were able to we have a discussion with the domain scientists, and they tell us, well, only 20% of the time do I want this suggestion to be sent if at this time there's no evidence that the suggestion is effective. Okay, as I said, we changed this Bandit algorithm in a number of other ways, but I really do want to get to this third bullet point. After the study's over, it's very easy to look at some of the data and to think that this algorithm is fantastic and it's personalizing. And as statisticians, we have to ask, is this spurious? So in general, in HeartStips, this generalization of the Bandit algorithm was run online separately on each of the N users, N equal 91 in this particular setting. And here's some first questions that I might want to ask. So I have the data in front of me, the study's over. Is there some evidence of an average across all individuals, a treatment effect on the 30-minute step count? That's a natural first question. A second one is there heterogeneity in the treatment effect? Was it really a great idea that I ran this Bandit algorithm separately on every person, and thus I had to accommodate that heterogeneity? So how are we going to think about those questions, addressing those questions? So what we did, we couldn't find, there's really no work at this time. This is an area that's very new. And there wasn't any existing work in the statistical community or in the CS community, machine learning, to how to think about this. And what we did was we went back to classical clinical trials, very old, from last century, and we use meta-analysis. So meta-analysis is different from meta-learning, okay? It has some similarities, but it's different. So I give you a reference at the very bottom of this slide. You can see the references from 99. That tells you how old this literature is. And in this case, what happens in that setting, in meta-analysis and classical clinical trials, what one is doing is you have multiple clinical trials with the same, usually a drug, being tested, and you want to combine results across those clinical trials. So here in our setting, we're going to view each user as a clinical trial. Each user will have their unknown vector, 5-dimensional vector of treatment effect coefficients. That's and it's unknown, it's the true vector. That's why it has a subscript of 0 on that slide. And we're going to estimate that vector for each user by their posterior mean. And as we know, we're in a Gaussian setting with a Gaussian prior. This is the same as estimating the unknown vector by a ridge regression estimator, L2 penalization. Now, in classical meta-analysis, there's 2 ways that people think about these problems. The first way is you're only interested in the 91 clinical trials, in our case, users in front of us. We're going to only make comments about these users. And what one does then is one assumes this ridge regression estimator over either 450 time points or even more, to over 1,000 time points, has an approximate normal distribution where the mean of that distribution is the true that user's treatment effect coefficient, and some variance covariance matrix. This actually makes good sense in this setting. Remember, the Bandit algorithm that we're running is not a regret minimizer. It just attempts to reduce regret. So you always have some exploration. The randomization probabilities are always between 0.2 and 0.8. A second way to think is think more broadly. These 91 users, these N users, are a sample from some larger population. And in this case, this made a lot of sense because this study was run at Kaiser in Seattle in Northwestern United States. And this is a large healthcare organization. And people were recruited when they were first diagnosed with stage 1 hypertension. So if Kaiser wants to use an app of this type for its newly diagnosed patients, this would be the population we'd be interested in. In this case, you think more of a random effects type of point of view. And in particular, each user's 5-dimensional treatment effect coefficient is is a sample from some overall population. The overall population has some mean, 5-dimensional mean, and some variance, user to user variance. Okay, so we started to the first question. So this question is about population inference. So this is about the larger group of people with stage 1 hypertension. And in classical, we just use the ideas straight from classical meta-analysis. And in particular, what one does is one gets a weighted average of each user's treatment effect coefficient. So this little e, this is a vector with 1 and 1 entry and 0 everywhere else. It's one hot vector. And all it's doing is it's picking out each feature in turn. And the features are listed in that green table. So there's 5 features, their overall action, and then the interaction terms. The context, the current context was what was there, was an prior dosage, which was exponentially discounted number of suggestions that had been sent recently over the past week. Engagement, whether or not the user was working with, was looking at the app all of their own volition. Location, is the user in a structured environment currently or a less structured environment? And step variation, how variable their activity has been around that time over the prior week. So again, each one of these estimators is a weighted estimator of the individual specific coefficients, and these weights are just from the variance components. And this is, like I said, it's classical meta-analysis. And you see from the table from the first row that indeed there does appear to be some positive effect, increasing step count when you send a suggestion versus not. That's great. But when you go to the second row, you realize this is not, you have to be very careful when you make the prior statement, because if the coefficient for dosage interaction is negative and highly so. And indeed, what that means is that if the individual has had any very much dosage, very much recent number of suggestions, there doesn't appear to be effect on their step count. This is very depressing. And this emphasizes it even more fully. So let's say the user is in this particular state. They've experienced their recent dosages at the average level. They're currently engaged. They're looking at the app. They're at home or work structure. That's a structured environment. And their recent variability and activity is low. Then you can use this weighted average and form a confidence interval. And you see, indeed, the data does not provide a lot of evidence for there being an overall average effect across all users of sending a suggestion versus not. So now we're going to look at treatment effect heterogeneity. Is the better action user specific? And in classical meta-analysis, what one generally does is switches to the finite sample. We're just looking at these 91 users. Is there evidence that among these 91 users, there's differences in effects? So what we do here, and again, this comes straight out of that literature, that tutorial that I showed you earlier. We take each user's treatment effect and we subtract from that an average treatment effect. So each user's treatment effect, the average, and we get the variation. The average is a weighted average, weighted by the within user variance. One compares this to a chi-squared on n-1 degrees of freedom. And here you see the results. But of course, let me just remind you, the null hypothesis is there's no treatment effect heterogeneity. That is, this coefficient of weights, the 5-dimensional coefficient of weights, it's equal for all 91 users. When you go to that green table, you see, indeed, there's a good bit of evidence that the treatment effect there's a lot of treatment effect heterogeneity. I was pretty surprised at this, to be honest. So here's a natural question, if you're familiar with the field of reinforcement learning, is on average, does the Bandit algorithm, this generalization of a Bandit algorithm, select more effective actions than if we just use the prior distribution and formulated a the policy for choosing decisions. So to understand what I mean by more effective, first I'm going to define the average reward. So the average reward for a policy on user I is denoted by this V sub I. Pi is the policy. So the policy can be from the prior. The prior can be used to produce a policy. And you see that it's expected average reward for that user. This expectation is an average over that user's states, the states that user experiences, as well as any stochasticity in the policy. And the policy derived from the prior is a stochastic policy because you use prior probabilities to decide whether or not to send a suggestion or not in a given state. Now the estimator of the user I's average reward under the Bandit algorithm, here we got to recognize the Bandit algorithm is learning. So it has a different probability of sending a suggestion as time goes on, even if the individual were in the exact same state. So, but it doesn't matter because all we need to do is take the average of the rewards we see in front of us for this user. And then to estimate the average reward under the prior policy, we use importance weights. More sophisticated estimators have been developed for this setting, but here we kept it very simple. So we didn't use, for example, a doubly robust estimator. We just used importance weights. Okay, so now we put it in our meta-analysis setting. So each user's theta, now it's a scalar theta, is the comparison of the value under the Bandit algorithm minus the value, the average reward under the policy formed from the prior. We don't observe theta sub 0 I. Instead, we estimate it by the difference between the estimated values. In our setting, because we are continually exploring the randomization probability state between 0.2 and 0.8, this theta hat I has we can approximate it with a normal distribution. So if we focus just on the 91 users, that's what we'll do. If we want to have something, if we want to make a statement about overall, the entire population of individuals with stage 1, newly diagnosed stage 1 hypertension, then we additionally make that second assumption, that the true scalar difference in values varies normally across the population. Okay, so the first question in this particular set is, does the Bandit algorithm result in higher rewards than the prior? So this is on average across the entire population. And indeed we see, yes, it does. We get an average higher performance. And this is thought to be the case because the Bandit algorithm doesn't overtreat. Remember when I discussed the prior, I said that the first entry in the prior means was the prior mean was positive, because on the original heart step study, we did see a strong effect of treatment, sending a suggestion. So the prior essentially sends too many suggestions, and the Bandit algorithm backed off on that. Also, if we start to look at treatment effect heterogeneity. So does the difference in values, is it the case that for some users, it's really worth running that Bandit, and for other users, it just doesn't matter? And indeed here, that's that lower table, you get gross heterogeneity, indicating that for some users really appear to have benefited from running the Bandit algorithm. So I have 2 more questions. These are more exploratory. On average across users, does it appear that this algorithm learned over time? Now, our prior was an informative prior, and our prior stated that the treatment effect of sending a suggestion versus not is positive. And we already saw from our analyses that the data does not indicate that that's the case, that the treatment effect on average across all users is positive. So what we're expecting here is we want to see, well, did the algorithm learn this fast? On average across users, did the algorithm quickly learn that there's really actually, on average, no treatment effect? Okay, so to do this, we use a bootstrap procedure. So the first thing is this blue curve that you're seeing, in particular, if you focus on the graph on the left-hand side. This is the actual data from the study. It's the average posterior mean of the treatment effect in a particular state, and the state is given to you in the second bullet point. So what we see, if you can see it, the blue curve starts around 0.47. That's that prior mean of the overall effect. And then it goes down pretty rapidly across time. Now you could ask, is that rapid decrease just noise? So to think about that, we ran these bootstrap experiments. So there's 2,000 black curves, each corresponding to a bootstrap trial. Okay, how did we form a bootstrap trial? So in each of the 91 users, what we did was we subtracted from their reward, we subtracted their treatment effect in the particular state they were in at that particular time to get what we call a residual. It's not mean zero because we're only subtracting the treatment effect. But for that individual, we now have state residual, state residual, state residual over the entire duration of time that individual was in the study. We then randomly sample. We obtain a bootstrap sample of 91 users, so 91 trajectories of state residual, and we run the Bandit algorithm on each trajectory separately. The Bandit algorithm will see a reward equal to the residual if the Bandit algorithm chooses no, do not deliver. If the Bandit algorithm chooses deliver the suggestion, then the Bandit algorithm will see the residual plus the treatment effect, the prior mean treatment effect. So the black lines are all under the ground truth that the treatment effect is in accordance with the prior mean. Every single one of the 2,000, because there's 2,000 bootstrap trials, each of 91 users. And you see that if you look at how the performance of the posterior mean in each one of those Bandit studies, they form a cloud, and it gradually gets a little narrower at the end, but it pretty much stays horizontal. And very rapidly, now we see that the blue curve, the actual curve from the study, drops below that line pretty quickly, probably by time 40 or so. The earlier drop, the immediate drop, is well within the mass of black lines. And so you can't really say much about learning, say at time 20, for example. The second figure on the right-hand side is just a sanity check. If the posterior mean for each individual was the ground truth, then would the blue curve stay within the mass of the bootstrap studies? And indeed it does. Okay, so this is my last question I wanted to ask, and this actually is the reason why, this question is the reason why we actually started going down this path. And it's the reason why it emphasizes the fact that AI can be so dangerous and it's so easy to be misleading. So we had quite a number of users where when we looked at that user's data, it looked like the user was experiencing the Bandit algorithm was personalizing to that user in a very interesting way. And I'm going to show you a graph of one particular user on the next slide. The question, of course, is this just spurious? I mean, remember, the algorithm itself is a stochastic algorithm. So here's a particular user. The horizontal, the x-axis is the date in study. So this user joined this study in mid-November 2019, and left the study, ended the study in early August 2020. This is in Seattle, and Seattle shut down because of the pandemic around March, late March. So you can see this spans that entire period, pre the pandemic shutdown to post the pandemic shutdown. The dots are each dot is the posterior mean of the treatment effect in that individual's current state divided by the posterior standard deviation of the treatment effect in that individual's current state. And why am I looking at this ratio? Because this ratio translates directly into the randomization probabilities. The higher the ratio, the higher the probability the user is sent a suggestion. The lower the ratio, the lower the probability the individual is sent a suggestion. So you can see each dot, and you see the line, the horizontal line, 0. So there are many times in which the algorithm is not seeing any evidence that there's currently going to be a treatment effect. Okay, so there's 2 colors for the dots. The blue dots are when the individual has been looking at the app without us prompting them. The red dots, that's the engaged state. The less engaged state is the red dot, and that's when the individual just hasn't been looking at the app at all recently, in on the prior day in particular. So if you look at this, you begin to, the immediate thing, like if I show this to a collaborator, they're going to say, whoa, this is the fact that the blue dots are almost always above the red dots means that we really should be sending a suggestion only when the user is already has been engaging with the app anyway of their own volition. And the question to ask is this spurious? Is this a spurious conclusion? So what we did was we did another bootstrap study. So the blue curve is the actual data. It's the user's posterior mean for the effective engagement as the study progresses. So you can see the blue curve. So now the blue curve starts at 0 because the prior mean for engagement, effective engagement, was 0. So that's why the blue curve starts at 0. And then you can see it moving through time. Each of the 2000 black curves is a bootstrap version of that particular user. And the way we get a bootstrap version of that user is we take that user's state residual trajectory, and we bootstrap the residuals. And then we run the Bandit algorithm on the resulting pairs. So now the resulting pairs now is state, a new residual, a bootstrap residual, state, a bootstrap residual, state, a bootstrap residual. And we run the Bandit algorithm. And if the algorithm says send a suggestion, we add back in the posterior treatment effect at that time, except we ensure that we set the coefficient of engagement to 0. Okay, so if you look at this, at the beginning of the study, even though it was very tempting to conclude that one should only send these suggestions when the individual is engaged because that's when they're most responsive, the blue curve is well within the mass of the black curves. Maybe at the end, like in June of 2020, the blue curve starts to drift above the mass of the black curves, indicating that indeed, perhaps there is evidence that, so this is this period of time right in here, that there's sufficient evidence that it's better to send it, it's more effective to send the suggestion in the state of when the user is engaged. Okay, this is my last slide. We used a sequential decision-making algorithm, but did we achieve personalized digital health? Here we assumed that each user is a classical Bandit environment. By that I meant their states are not affected by prior treatment. And that's probably not true. But even if you are willing or you're comfortable assuming that, how would you do a better job assessing whether or not personalization occurred? There's just not a lot out there to do this. This is a completely open area of statistics. If the Bandit environment is violated, say we have in fact a Markov process, How do you assess personalization in that setting? We don't know. How do we do this? Okay, thanks so much. Thanks for joining me for these 40 minutes. It would be great to hear from you. Take care. Enjoy the conference. Bye.